Hello students, you are most welcome on this YouTube channel. Equivalent circuit of transformer that we are going to discuss now. As we have already discussed in the operating principle of transformer, what is a transformer? Transformer is a static electromagnetic device that transforms electrical energy from one circuit to another circuit at a constant frequency through mutual coupling, right? And it is used to step up or step down the voltage, to increase or decrease the voltage, right? So obviously transformer deals with the alternating voltages, right, and not with the DC voltage. All these things we have already discussed in the operating principle video. Please watch that video on operating principle of the transformer, right? So right now we are discussing the equivalent circuit of the transformer. So the circuit that I have drawn in the operating principle of the transformer, that was basically physical circuit showing the windings of the transformer, showing the core of the transformers, right? Physically we are showing the windings, copper windings on both limbs of the transformer. Physically we are showing the iron core, right? And that was basically physical circuit. Now just by looking at the physical circuit you cannot analyze the circuit, right? So to analyze the circuit and to do the various calculations and to determine the voltage regulations, to determine the efficiency, to determine the losses, and all these calculations we need, for all these calculations we need an equivalent circuit, an electrical equivalent circuit. So the physical circuit that we have studied, we will convert that physical circuit into its electrical equivalent circuit, and that electrical equivalent circuit will be used for the purpose of analysis of all these parameters like efficiency, voltage regulation, losses and all, right? So we have seen that in the physical circuit we have two windings for the single phase two winding transformer. One is called as primary winding, another one is called as secondary winding. In between the primary and the secondary winding we have iron core, right? Windings are made with copper windings, right? Winding means inductor, winding means inductor basically, right? So inductor means it is having some inductance L and some residue resistance. Every inductor, if you see, it is not pure inductor. Practically it is having some small value of resistance, some residue resistance, right? So inductor means it's a series combination of resistance R and inductance L. So that is the meaning of winding, right? So we are going to draw the primary winding electrical equivalent circuit, right? So here first of all you see that to represent the copper winding, primary copper winding, we will represent it by a small resistance R. First you make the circuit, right? This V1 is the applied voltage, it is the symbol of alternating sign, it is a sign of alternating current signal. So V1 is the applied voltage, or you can say source voltage. V2 is the load voltage, that is also alternating, right? So either it will step up or step down the voltage, either it will increase or decrease the voltage, right? So primary winding will be represented by a small, very small resistance, right? This is the symbol of resistance. Let me call this is R1 For primary winding side, we are representing by suffix n1. For all the quantities, right, which are primary side, they are represented by suffix 1, and for secondary side we will use suffix 2, right, for all the quantities. So this is the primary winding resistance R1. Now we will also have an inductance, right? So this is the symbol of inductance. Everybody know this. So this is the inductance, primary winding inductance. Let me call this is L1, right? And if you want to represent the ohmic value, then you write XL1, right? XL1, isn't it? Or simply X1. X is inductive reactance, which is equal to 2 pi FL. F is a frequency, 2 pi is a mathematical number, L is an inductance. So you can also write it in place of L1, you can also write it X1, right? That is primary winding parameter, right? So X is 2 pi FL1, right? So this is the representation of primary winding resistance with the inductance, right? So now to represent the iron core in between the primary and secondary winding, we will have a shunt branch consisting of an inductance like this. So this inductance is basically known as magnetizing inductance, which is responsible of magnetization of transformer core, and Rc is basically representation of core losses, right? So the current which is in primary winding, that is, we call it as a I1, right? Current which is flowing in the shunt branch is basically no load magnetizing current, or basically you can call it as a exciting current IE, or it is also represented by I naught, that is basically no load magnetizing current, right? Exciting current or no load magnetizing current I naught, IE or I naught. So I naught, I told you that it is 2 to 6%, 2% to 6% of the full load current. So for example, if I say if the full load current is 10 ampere, then what should be the exciting current or no load magnetizing current? It is 2% to 6%, somewhere in between this range. So that means exciting current for 10 ampere full load current will be 0.2 ampere to 0.6 ampere, somewhere in between this range it would be, right? So for 10 ampere full load current, the exciting current will be 0.2 ampere to 0.6 ampere. That means 2% to 6% of the full load current. That is the typical value of exciting current or no load magnetizing current in case of single phase 2 winding transformer. So we have discussed this in the earlier video. Please do watch the earlier video, right, on the operating principle of the transformer on the same YouTube channel, right? So Xm is the magnetizing inductance which is responsible of magnetization of the core. Rc is the representation of the core loss, right? So it is represented by R suffix C. Remember, C here represent the core and not copper, okay? C means, suffix C means core and not the copper, right? Now the current which is flowing in this winding, in this branch XM is IM, that is basically corresponding magnetizing current, and the current which is flowing in this core loss resistance is basically IC, that is a core loss component of the current. So you know this, all these are AC, right? AC values. This voltage is AC voltage, V1 is AC voltage, V2 is AC voltage, IM is AC current, IC is AC current, right? So transformer means AC, we deal with AC. So no job of DC here, absolutely not, right? I told you the reason. Please do watch that video because it cannot work on DC. Transformer always work on AC only, right? So to represent AC, let me give a phasor notation, that is IE phasor, I0 phasor, I1 phasor, IM phasor, IC phasor, right? Okay, so here this is the electrical equivalent circuit, R1 and X1 for primary winding side. This shunt branch represents the core iron the iron core. This shunt branch or parallel branch, shunt means parallel branch represent the parallel branch is the representation of the iron core, right? Now here this X1 is basically leakage reactance. X1 is the leakage reactance of the primary winding. X1 is equal to 2 pi F into L1, right? L1 is the primary winding inductance. So this X1 is a leakage inductance. Now here let me draw the windings of the transformer. This is the primary side winding, this is a secondary winding, right? So the induced, we have already discussed the operating principle of the transformer. The induced EMF of the primary side, let me represent it by E1, right? So this dot and this dot shows the same simultaneous polarity. That means if at one particular instant, if this point is positive, then this point, this dot is also be positive, right? Correspondingly this end will be negative at one particular instant. So dot convention means dot shows the same simultaneous polarity. That's the meaning of dot convention. So plus minus E1, here it is plus minus E2, induced EMF in the secondary winding, that is E2. E1 is the induced EMF in the primary winding, right? These parallel lines, these two parallel lines represent the iron core, right? Parallel line in between these two winding, it represents the iron core. Had it been the air transformer, air cooled transformer, then in that case you should not draw these two parallel lines. But since it is the iron core transformer, so it is must to draw these two parallel lines. That is the convention. That's how we represent the iron core. Two parallel lines in between these two windings, right? Like that. So here, now likewise secondary winding, we can represent the secondary winding, secondary copper winding by resistance and inductance. So here secondary winding inductance is basically L2, or the reactive part or reactance or leakage reactance of the secondary winding will be X2, right? It will also have some residue resistance, some small resistance, that means R2, right? Okay. secondary winding current will be I2, right? Secondary winding current will be I2. So here you see that this side is secondary side, this whole side is basically secondary side, right? And this side is basically primary side, right? So I2 is a secondary winding current, or you can say load current, right? So load is connected on the secondary side. At this terminal we are connecting the load, right? So you can show the load on the secondary side, right? Load on the transformer is basically electrical load. Alright, so this I2, you can refer the secondary side quantity to the primary side, right? Or primary side quantity to the secondary side, right? For ease of calculation, to simplify the calculation, you first make one combined equivalent circuit for ease of calculations. So for that you need to refer one side quantity to another side. So either you can refer primary side quantity to the secondary side, or you can also refer secondary side quantity to the primary side, right? So I am referring the secondary side quantity to the primary side. That is the most common method to represent the transformer equivalent circuit, by referring the secondary side quantity to the primary side. So secondary side current is I2. Let me make here, it is I2 dash now here, right? So by the turn ratio you can represent, right? Dash means it is referred value, right? So basically turn ratio means it is referred by, it is a ratio of number of turns, right? So by the ratio of number of turns you can refer the quantities of one side to the another side, right? So the turn ratio or the transformation ratio is represented by N is equal to, this is V1 by V2, or that is equal to E1 by E2, or that is equal to N1 by N2. N1 is the number of turns in the primary winding. N1 is the number of turns in the primary winding. N2 is the number of turns in the secondary winding. E1 is the induced EMF in the primary winding. E2 is the induced EMF in the secondary winding. V1 is the supply voltage, primary side voltage, source voltage. V2 is the load voltage or the secondary side voltage. So N1 by N2 is known as turn ratio or transformation ratio, and that is equal to I2 by I1. Current I2 secondary side current, I1 is primary side current, right? So that's how we can refer the secondary side quantity to the primary side. So that means if I say I2 dash, that is basically secondary side current referred to the primary side. So I2 dash, or you can say it will be I2 dash is equal to I2, and here it will be referred by the transformation ratio. So here it will be N1, not N1, this is N2 N2 by N1 like this. So similarly, if you refer the secondary side induced EMF on the primary side, then you will write E2 dash is equal to E1, and here you will write in bracket, you will write N1 divided by N2, right? So like this you will refer the secondary side quantity to the primary side, right? So here I'm sorry, this is, you just rectify this is not E1, this is E2, right? E2 dash is equal to E2 N1 by N2. Right? So, and also the ohmic values will be referred by the square of the turn ratio. Okay. So that is basically equivalent circuit of the transformer, right? If you combine secondary winding with the primary winding, right, then it will be the equivalent circuit, right, referred equivalent circuit. If you refer the secondary side quantity to the primary side, it will be the equivalent circuit of the transformer, right? So you can draw the equivalent circuit of the transformer. So referring the secondary side quantities to primary side and making the equivalent circuit of the transformer. So for the ease of calculation we are doing this. So just refer the secondary side quantity to the primary side. You can also refer primary side to the secondary side, but I am preferring the common method, that is to refer the secondary side quantity to the primary side. So the circuit will be, equivalent circuit will be like this, R1, and here it is this is X1, right, leakage reactance X1. This is the representation of the iron core. This shunt branch represents the core of the iron. This is the magnetizing reactance Xn, magnetizing current Im, core loss resistance Rc, core loss current Ic, right? And when you refer the secondary side quantity to the primary side, you will write like this. This is secondary side leakage reactance X2 dash, and here this is the primary side, secondary side resistance of the winding R2 dash, right? All right, secondary side current I2 dash like this. All right, so this is the equivalent circuit of the transformer, right? This is the primary current I1. Here it is supply voltage V1. Here it is load voltage V2. Here it is load voltage V2. Okay, so R2, I2 nx2, these all are referred co-E2 dash, these are all the referred side, referred quantities. Right. So here E1 and E2, they are produced by the same flux, same mutual flux phi m. So they will be in the same direction, right? So if I say N1 is equal to N2, number of turns, if they are same, N1 is equal to N2, then induced EMF will also be the same. Magnitude of the induced EMF in that case will also be the same. Mod E1 is equal to mod E2 if N1 is equal to E2. If N1 is equal to N2, if N1 is equal to N2, then magnitude of both the induced EMF will also be the same, right? Now exciting current IE, that's what you call it as a no load magnetizing current or exciting current IE. This excitation current IE, it will lag approximately by 90 degree, right? It will lag approximately by 90 degree from E1, right? From minus E1, right? Minus E1 because minus is due to the Lentz's law, right? So it will lag, IE will lag approximately by 90 degree from minus E1, or you can say, since this is IE is produced by the flux phi m, so it will approximately be in phase with phi m, approximately I am saying, right? So now we can draw the phasor diagrams of the transformer.